Yes. By way of introduction, because we have been discussing, we have been hearing stratified analysis, stratification as one of the ways to remove confounder. But it's not only the confounder you even remove through stratified analysis. You can actually check for that thing like effect modification, which they call different name, interaction, whatever. Now, but they agree with me that the stratified analysis is not as popular as maybe used to be. And the reason is very simple. Most of those statistical methods that were maybe we were using before have been taken over by regression, because what they can do, regression will do better. And where they are limited, there's limitation, regression will take hold of it. Just the way ANOVA will soon fade out and give room for linear regression. This analysis, not that it has faded out, it has given room for logistic regression. But however, it's good to understand the concept. So today we'll be looking at statistical analysis. And later you discover that you don't even need to do it. Regression will solve the same problem. Yeah. Two different analytic concerns motivate the division of data into strata. You know, it's just when you divide data into strata, you say stratified analysis. What it just means that you divide them into different groups and analyze them separately. For example, if socioeconomic status, you have three groups. You can divide your data into the three, upper, middle, lower, and do your analysis. Do your any analysis you want to do, calculate your chi-square separately for each level. Just like the way you have three groups or two groups, you do it separately. So stratified analysis just means that you are using a particular one variable as to create a strata, and then divide separately and now analyze separately for them. So there can be more than one variable at a time that you use. In that case, you are going to have many strata. Just like it's similar somehow to ANOVA. The problem posed by ANOVA, and the same thing with the stratified analysis. Just like what I said before, is taken over. The role is taken over by logistic regression. Just like the role of ANOVA is being taken over by linear regression. So, two analytic concerns: the need to evaluate and remove confounding. That's one major. Why should people do stratified analysis? To remove confounding. We talk about confounding also now. You need to discover and describe effect modification. So two things: confounding, you evaluate it and remove it. Then you are not removing effect modification, it's just for you to describe it. You cannot remove it. So to discover and describe effect modification. All these two also can be analyzed using other methods like regression. Even if we are dealing with, if you remember what that were in ANOVA workshop, we talk about interaction when we discuss, we did run factorial ANOVA. You remember the data where we have a bear goggle effect, where people were choosing mates and the male and female. So we try to, and we discover when we run the ANOVA, we saw the interaction effect of the sex and the alcohol. So it's the same thing here. So the interaction is the effect modification. Stratified analysis or stratification is used both to control for confounding, discover and describe effect modification, and requires separating sample into subgroup or strata according to the confounder of interest or the variable that's causing the modification. Example, the commonest confounders are social, demographic, and socioeconomic variables: age, sex, ethnicity, race. Yeah, that is why you discover that hardly is there any study you did you do that you will not have session for them because they are potential confounder. The work is not done unless you have control for them. I will reduce the volume. Now, confounding. Let's describe what confounding means. It occurs when a variable is associated with the exposure and it affects the outcome. Can you see? It affects the outcome. Look at this, the diagram below. This diagram is self-explicit. The variable of the outcome of interest, the disease, and this is the exposure, the relationship between the disease and the exposure and the disease. That one horizontal, that's what you're interested in. But there's a confounder, the one at the top, is associated with the exposure in the sense that they are related. If you look at the arrow, whenever you are drawing the confounder and the exposure, they have two-way arrow. It's not as if one lead to the other or this only, but they are just associated. Somehow, they have something in common. Not that one is causing the other. No. That is why the arrow is from both sides. They are just associated there. Somehow. Why the exposure to disease, that is causal arrow, one-way arrow. And the confounder also is a causer. It causes the disease also. Can you see? So you are having two things that are causing the disease. You are only studying one, which is the exposure, which we call exposure. But the other one that is causing also is also associated with the exposure. So you can think in that light. To make it simpler, look at the next one. This one now is not specific, and the other, the next, you want to make sugar and make your, don't make noise. So, go inside. Relationship between coffee drinking, heart disease, and third variable, tobacco use. You see, the exposure here is coffee drinking, the outcome is heart disease. And the confounder is the tobacco use. Can you see? So, if coffee contribute to heart disease, tobacco also contribute to heart disease. Somehow, tobacco and coffee are somehow related or associated. If let's say you are studying the effect of tobacco on heart disease also, tobacco is your exposure. Coffee also will serve as confounder because both of them lead to heart disease. And somehow there, if you see the arrow also, between exposure and confounder, it's two-way arrows. Whereas from exposure to the disease, for the confounder to disease, is one arrow. That is the standard. So in describing confounding variable, that is the standard. Now, okay, before I elaborate much, there's the third one, yes. Just to create the mental picture. This is the relationship between alcohol use, lung cancer, and third variable, smoking. So what we are studying here is alcohol contribution to lung cancer. Of course, smoking also contributes to lung cancer. And alcohol and smoking are related. Somehow. Can you see the arrow? The arrow from exposure to the lung cancer is one-way arrow. From smoking to lung cancer, one-way arrow. But between smoking and alcohol is two-way. So if let's say your exposure of interest is smoking, so the alcohol also may serve as confounder, will be a confounder in that sense. That's just the explanation. Now, what I want to emphasize here is that this confounder is not an intermediate stage in the causation of the disease. It's not as if maybe the alcohol use will lead you to smoke, the smoking will not cause lung cancer. No. Or the other one, it's not as if maybe the tobacco will cause you to be taking coffee and the coffee now lead to lung cancer. Or maybe coffee will lead you to be taking tobacco and tobacco now lead to lung cancer. No. Or maybe smoking will cause you to drink alcohol while the alcohol lead to, or alcohol lead you to smoke and smoking will not go. No. So the confounder is not an intermediate step. It's not as if maybe the relationship between the confounder and the exposure is that exposure leads to that confounder, and that confounder now leads to the outcome. That one, if is that case, that is a confounder, it's a causal pathway. It's part of the causal pathway. One thing lead to this and that lead to this. And just like when you are talking of obesity will lead to something, something will lead to another thing. You know, there are something that some of those things that are causing cardiovascular disease, one thing lead to the other. Something can lead to obesity, can lead to something, and that particular thing will lead to the heart disease. That one is different. So I think we have the mental picture of what a confounder is. I don't know if there's any question, because that is the tradition when we are doing our workshop. It's not the public lecture like Tuesday and Thursday. This is a serious business. So I want everybody to have mental picture before we move ahead. So I think we should have mental picture of confounder now. What confounder is. Is there any question regarding that? Any question? So we proceed. Okay. If you, I don't know, if you have question, you can raise your hand, or you can just talk, or you shout. Okay, let's proceed. Now, removing the confounder. Well, though almost the same with the we discuss the fair motivation very soon, but let's just look at how do you remove confounder. This is just 5 ways to remove confounder. 3 are what you deploy at the design stage. The last 2 are what you do during analysis. So it's the last 2 that concern me most. The other one also, well, they are process, they don't really just what you do, randomization. When randomization means just selection into different groups by chance. Just by chance, that is, you just use balloting or whatever to ensure that when somebody is selected into group A, group B, group C, or whatever group, it's just by chance. It's not because of any other thing. That is randomization. And it's used a lot in experimental design when you randomize into control experimental group or different treatment group. You know, but one of the issues with randomization is that if the sample size is very small, if the study is not big enough, even when you do randomization, one group can still be different systematically from the other group because the sample size is not more. But if the sample size is more, you do randomization, somehow, the effect, you discover that if you by chance you select into different and the sample size is large, in all respects, both sides will be almost the same. But the effect of that randomization is not marked, it's minimal when the sample size is very small. Just like you remember when we talk about probability. If you say you toss a coin, you say that what is the probability that is the head? You will say 0.5 because 1 out of the 2 faces favor head and the other side favor tail. But if you toss a coin 10 times, all of them can be head or tail. Or most of them will be head or most of them will be tail. You can only achieve that 50-50 if 50-50%, if you toss it thousands of millions of times. You toss it many times. By the time you see, even though the figure may come out differently, but by the time you calculate the percentage, it will be 50-50, approximately. So can you see now? So that is why in randomization, before you can say the 2 sides are the same in many respects, the samples are usually have to be. Then restriction, meaning that for this case now, that maybe we are studying this way of smoking and alcohol. If you don't want to study the effect of alcohol on lung cancer and smoking is a confounder, you can say no smoking. No smoking involved. Anybody that's smoking is not part of the study. That is what we mean by restriction. You have restricted your participant to those that are not smoking. In that case, if you didn't recruit anybody that is not smoking, there's no way smoking can confound again. That is restricted. Then the other one is matching. What you can do is to make sure that you match for the confounding variable. Like for this case of alcohol as well, make sure, okay, if somebody is smoking in the group that is the case, or if it is cohort study, the group, all this studying the effect factors is analytical study. You use analytical study to study factors. You don't, even though you can run factors with a descriptive study, but actually, you want to see analytical, descriptive, comparative study, you can still do that. But most of, even the comparative study, there are two groups. Yes. So when you are calling out analytical study, most of the time you want to know the effect of a particular factor on the outcome. Analytical study. So you have comparison group. So matching means that one group, if one group, there is one person that is smoking, you make sure the other group, there will be another person that is smoking. So eventually, if you have sample size also and 30 people are smoking on one side, you have our 30 people smoking on the other side also. So in that case, you have match. So meaning that the confounder are the same on both sides, so it will not affect, the effect is even on both sides. Then those are the methods you use during design stage when you are starting your study. But if you have done the study, all those things are not be done, or you have done them maybe still not perfectly, during analysis. And most of the time, the restriction, matching, randomization is many things that the experimental design, they do a lot because they've already made up their mind. And since they can perform the experiment, it's better to make sure that everything is intact, obey all the rules to remove restriction and to remove effect of confounder. But of course, now you know that it has its own disadvantage also, because at the end of the day, experimental research, the finding has high internal validity, low external validity, because it's valid for the group you study, but it's not so valid for anybody outside. Because, for example, you do experimental design to know the effect of a particular treatment, and most of the time, exclusion, in trying to do restriction to control for another confounder. When you say exclusion, it's part of the restriction way of restricting. Exclusion criteria. You restrict epilepsy, no pregnancy, no sickle cell, no asthma. Every chronic problem, none of them should be there. But if it is, let's say it's heart disease you are studying, effect of maybe a drug on cardiovascular problem, and you restrict all those things. By the time you finish, what you have just got to study is efficacy. Efficacy means in ideal situation, not the effectiveness of the drug, because in the real life, people will have the heart disease and still have asthma. They will have the heart disease, they have sickle cell. They have the heart disease, they may be pregnant. Why they have the heart disease, they need the treatment, they may be pregnant. And many, many other things. So you discover that whatever after all those things, in experimental design, you just give evidence of the treatment in ideal situation, but not in the normal situation. And that is why when you do that, you still need observational study to follow up the effect of that treatment in the community. And sometimes the observational study in that sense can be more costly. More costly. Apart from the fact that people, I keep on saying it, I will keep on saying it. People have this notion that experimental design is superior to other design. No, it's not superior. The issue is that the evidence you get for the treatment is superior, of course. It's superior. It gives you the best evidence. You can really say, okay, you can really say, okay, this particular thing, it treats this thing, because we have removed a lot of confounder what can mask the evidence. give you the evidence. But the study design is not superior. It is by no way superior to the other one. And many a time, I keep on saying it, look at the issue of a low dose aspirin in treatment of cardiovascular prevention of death from cardiovascular disease. No, a lot of randomized control trials, supported that, and even meta-analysis, demonstrates that, and all over the world, prescribing aspirin, for people with cardiovascular problem. They not knowing that after it was later they discovered that more people die from bleeding disorder, for bleeding, than they will have even died from the heart disease. Because of course, when they were doing the aspirin, they know that the aspirin can cause bleeding. So anybody with tendency to have bleeding disorder was excluded, and many situations were excluded. So they just came with this situation, and that is not the normal situation. So at the end of the day, everybody received the treatment, not only the people the category of people that were in the study. So it was causing a lot of problems. That is why it's good after you finish the experimental design, you need observational study to follow up. So let's now come to the method employed in during data analysis. That's stratification and statistical modeling. You can be sure that it's more even mentally
hello.
demanding. Yes.
Hello. I have a question. Can you hear me?
I can hear you, sir.
I have a question. Restriction and matching, they are very clear, but I cannot understand how randomization can lead to removal of a confounder. I think it's better for bias.
We have discussed confounder is
because if you randomize, what is the guarantee that you remove the confounder? The confounder will still.
Okay, if you remember when we discussed, I was even thinking better when I was doing my slide. One of the things we may, we have discussed this potential error in measurement where we talk about bias. Confounding is a form of bias. Now, confounding is a form of bias.
Okay.
Yes. Okay. So how it removes it is this. If randomization just means that by chance you just put them non-randomly and make sure you don't. Imagine you knew that you are doing the study, you knew that you are studying alcohol on the effect of alcohol on lung cancer, and somebody that is smoking, and may more likely take alcohol also. And so you yourself, because if you actually, especially if the company that is sending you to do it, they are financing it, and you already made up your mind that it must be significant. You intentionally put all those ones that are smoking, you put them under you get a lot of people that are smoking that are taking alcohol. The people that are not smoking, that are not taking alcohol. Alcohol, of course, if it's case control you are doing, there will be people that have lung cancer and people that don't have lung cancer. So, but when you are recruiting, you make sure, okay, for the case control, we even know that, you have already got to the case. When you are recruiting your control, you make sure you remove anybody that is smoking. Yes, I mean now. You yourself, when you are recruiting, you are sure you will be recruiting. You make sure that in the control side, you try to limit those who are smoking, because you give the impression that because smoking also, that it has effect, exactly. So you make sure you remove it from that control. So if it is cohort, that one is even straightforward. If you know that alcohol, you recruit a lot of people that if they drink alcohol and they smoke, no problem, you put them. For the other control, the other side, you make sure that, of course, people that are not taking alcohol, you make sure the people that are not smoking, they are not the other side. You try to remove them. So in that case, you are affecting it. It will bias it. The confounder will be, the effect of confounder will be there. So if you just do it randomly, so it will help you to spread it. And I've already said it, that if the sample size is very small, the randomization effect may not be marked. It may not even do anything. Because the samples are somehow, it will still be tilted to one side. But the randomization make more sense if the sample size is very big. By the time you really do the randomization, you're going to see that by chance, it's going to be on both sides. If there's anybody that has the confounding variable, both of them will be spread on both sides. So that's how it removes it.
Okay, okay.
Yeah. So there's something that just came to my mind. I wanted to say, okay, why are we even saying that the confounder that the confounder and the exposure, they are related? How? You know, look for example now. Look at the smoking and alcohol. We know it's not everybody that drink alcohol smoke. Some few people also, maybe they drink, they smoke, they don't drink. Like, if you pick somebody that is drinking, and pick somebody that is not drinking alcohol, the probability of the person drinking alcohol, taking cigarette is higher, taking tobacco. The probability of somebody taking tobacco is higher than the person that is not drinking, taking tobacco. The same thing, if you take somebody that is taking tobacco, the probability of that person taking alcohol is higher than the person that is not taking tobacco. So that is, can you see they are related? It doesn't really mean that if you do one, you do the other one. No, but it's like somehow. The other example about coffee and tobacco. No, coffee is sometimes used also in its own sense. So we know that a lot of people take coffee, they don't take tobacco. But if you are to compare the person that take coffee and the person that don't take coffee, and calculate the probability of taking tobacco, the person that is taking coffee, the probability will be higher among the people that take coffee. You're going to have more people that take coffee. Some of them will take tobacco than people that are not taking tobacco, because it has to do with substance use. So that is just a logic. It's not as if one leads to the other, that if you are doing one, you have to know. But somehow, more like a social issue. So if you are doing one, you are likely to do the other one. So they are related. I mean, both of them are causing the same, contribute to the same disease. So both of them will serve as confounder to one another. And about the issue of social demographics variable standing as confounder. For example, I was seeing one of our lecture, one of our workshop, that I observed something, or is this somebody's work? I don't remember. Age and okay, somebody's work that you're discussing with. Age and education. They were related to knowledge of something. The more the higher the age, they study women, maybe women of reproductive age group, and they are trying to look at knowledge of and depression score and the knowledge of depression also. It is all that as the age increases, the knowledge increases. At the educational level increases, knowledge increases. If you can look at both of them, they can conform to one another, because they have age group 18 to 20 something to 30 above. You know, somebody that is older, around 30 and above, he will have, those are the people that will have had time, by virtue of it, will finish secondary and tertiary education. The person that is 18, maybe the person is not likely to have finished even, maybe has finished tertiary secondary education, but finished tertiary, may not. And if the person also married very early, maybe the person didn't even finish primary school. So you see that having formal, no formal, primary, second, tertiary, even sometimes people postgraduate. So somehow the age relate to the level of education. So when you see age is significant, level of education, it may be the level of education is significant. Age is just happened that it happened that the older people have higher education. So to now say that as age increases, the level of knowledge or the depression score or whatever, level of knowledge increases, it's not true. So that is the essence of the moving confounder. I think we move on. So stratification and statistical modeling, that is what now used during data analysis. We have discussed what you use during this thing. because most of the time, and this one happen a lot with observational study, because there are situations, most epidemiological study are observational, because it's not ethical to do experiments, some experiment in certain situations. So there are a lot of experiments you cannot do on human being and in some situations. So you just have to study people in their natural state. Like now you cannot be doing an experiment and say the effect of smoking on lung cancer and give people the cigarette to be smoking. So you cannot do that. So you just have to rely on people that are smoking on their own. Nobody forced them. People that are not smoking and now look at the effect. So the observational study you cannot. So all those research, especially randomized, all those some may not work much. But during data analysis, you do stratification and statistical modeling, which is regression. And those are the things we are going to be discussing in this workshop. Then let's look at effect modification. We have just finished discussing, giving overview of confounding. Effect modification refers to a change in the magnitude of an effect measure according to the value of third variable after exposure and disease, which is called an effect modifier. So sometimes something that you call confounder may not be a confounder, may be an effect modifier. It's a third party also. But this third party differ in the way it is. What happens that along the gradient of the exposure, that third variable have different value. What do I mean? Okay, for example, people talk about they say there's correlation somehow have between drowning and ice cream sale and drowning. So does it mean that the ice cream sale lead to drowning? But the confounding factor there is the weather. Around the time, the ice cream, around the time of the ice cream scale, during the hotter, of course, during the hot weather, when weather is a little bit not too hot, people may not likely demand ice cream much. And at the same time also, people will not likely go and swim. But when the weather is hot, that is when people demand for ice cream, and also people also go to swim. So the effect modifier is not confounding in the sense that it's not as if the relationship between the effect modifier and the exposure is in such a way that there's a different gradient of the effect modifier along the different level of the exposure. Now, effect modification is an elaborated description of the effect itself. It is a finding to be reported rather than bias to be avoided. So it's something you report. It's not something. It's not bias that you are avoiding. Something you report. I think in our NOVA something class, there's fun interaction with some. Anyway, we'll discuss that later. So let's continue. When we use Martin as a method to control for confounding, we are making an important assumption, namely that exposure disease association is really the same in each of the strata defined by the level of the confounding variable. If it's not true, then it makes little sense to combine the odd ratio. So what this one just saying, what I just want to say here is that you have to first of all know if there is effect modification or that thing is effect modification or confounding. If you can find out that it's effect modification, there's no need for you to say you are controlling for confounding. That particular thing is effect modification. But if it's not effect modification, then it must be a confounder. You are now begin to look for this thing a confounder. Of course, when you are including the variable, maybe you may think, oh, it's a confounder, but you have to first of all do something to find out if it is effect modifier. If the effect of exposure on disease vary according to the level of confounding variable, then we say that the variable modify the effect of exposure on the disease. That was what I was saying the other time. if the effect of the exposure on the disease vary according to the level of confound. That variable you say is the third one. If based on if at different level of that variable, the effect of the exposure on the disease vary, then it's not a confounder, it's a modifier. So a number of different terms are used to describe effect modifier, effect modification. Effect modification, you call it, that is variable modify the effect of the exposure on the disease. Interaction, there's interaction between the effect of exposure and the confounding variable on the disease. So interaction, effect modification, it's the same thing. It is the same thing that has been described in different words. Heterogeneity between strata, that is different strata of the variable, the estimate of the exposure to disease association differ between the strata of that particular variable that I think is a confounder. But if the effect differ, that should that is effect modifier. What I'm saying in essence is that if it is a confounder, if you do your stratification, the finding should be the same for all of them. That is, if, for example, now you are studying the effect of alcohol on lung cancer and tobacco, smoking is a confounder. So among you that smoke, among you, if you do your stratification, you now analyze separately to look at association between alcohol and lung cancer for the smoker separately, and you do it separately also for the non-smoker. It should be the same. It should be the same because you have already removed, that is, for all these people, all of them are smoking. So if either the person has taken alcohol or not, all of them are smoking. So when you now compare, do people that take alcohol have more heart disease than the people that don't take alcohol? If you do it, you get the same thing. When you even do the same thing for the people that are not taking smoking also, because among them also you have people that are taking alcohol, you have people that are not taking alcohol. The issue, because you're going to calculate odd ratio or relatively, it's a ratio, so it gives you the same answer. So the odd ratio they are finding will be the same if that particular thing is a confounder. But if it is effect modification, it will not be the same. It will not be the same. Similarly, you may see tests for effect modification data as either test of interaction or test of homogeneity across data. So just for you to know that these three things, the same thing, effect modification, interaction, or heterogeneity. Now, before we talk about, because we are going to the real business now, how you remove, it's like a process, removing, trying to detect effect modification and trying to evaluate and detect and remove confounder is a step. From what I've been discussing before, you will know that the first step is to first of all remove effect modification. If the thing to detect rather, if you detect, okay, somebody's raising hand. Okay, Ugo, ask your question. Ugo.
Sir, thank you very much for this. Hello, I can hear you, sir. Can you hear me?
I can hear you.
Hello?
We can hear you.
Okay. Okay, sir. So I think I now understand. So the difference means that for the difference between confounding and then the effect modification is in the confounding, when you do it across different levels. So if you're stratifying it,
yes,
what you get should be the same, unlike in the effect modification.
Exactly.
Okay. So, and because I think, is that where that definition of it changes that magnitude? Is that what you meant?
Exactly.
Okay. Then are you, because I didn't get there. Maybe I wasn't here. But did you take the explanation for statistical modeling? How you can address it?
No, that is logistic regression will be going now, so there's no need.
Okay.
So
but did you explain
there are two ways we do Donny analysis: stratification and and statistical modeling. And statistical modeling, one of the other linear or logistic regression. So
that's the name. Okay.
yes, now modeling. That's not the only meaning. Even Poisson, our form of regression is modeling now.
Modeling. Oh, I didn't.
It's modeling. Yes.
Know that.
So yeah. So the test for effect modification now. The use of regression model to examine effect modification or equivalent is the most flexible approach. If you look at it now, what I'm saying is that no, I've already said before that even very soon, not very soon, you will see that you just hear of stratified analysis, but only will you see it in literature now. No, maybe it was popular before. So it's not as popular as regression, because regression will do better. So when we are using enzyme method to control for confounding, an alternative is to use chi-square test for effect modification. So what is it? You need to first of all test for effect modification before you even go ahead to do your this. This is equivalently and more commonly called chi-square test of heterogeneity. Can you see? So testing, we have already said that effect modification, interaction, heterogeneity mean the same thing. So when they say chi-square test for heterogeneity, you are testing for effect modification or interaction or whatever. So that's the first thing you test. If there is heterogeneity, that shows that there is effect modification. So that particular thing is not. So they usually say, okay, let's just continue. Under the non-hypothesis of no effect modification, all the individual stratum odd ratios will equal to the overall summary odd ratio. Can you hear now? If there's no effect modification, so that shows that thing may be a confounder, in that all the individual stratum odd ratio will be equal to the overall summary odd ratio. Now, test C for effect modification. Martin method assumes that the true exposure disease to disease odd ratio is the same in each stratum, and that the only reason for differences in the observed odd ratio between stratum is sample variation. So we should therefore check this assumption by applying chi-square for heterogeneity before reporting Martin-Hansen odd ratio. The test has low power. That's one of the major problems. The chi-square for heterogeneity has low power. It's surely unlikely to yield evidence for effect modification unless there are large differences between the stratum. So unless there are large differences, if there is small difference, you may not detect it. A likely value does not therefore establish absence of effect modification. So in fact, as the true odd ratio are never likely to be exactly the same in each stratum, effect modification is always present to some degree. Most researchers will accept, however, that minor effect modification should be done in order to simplify the presentation of data. So that is why, okay, because I don't want to say something that because we are still getting there. So approach to examining for effect modification now. Always examine the pattern of odd ratio in the different strata. How different do they look, and is there any trend across strata? Can you see? So we already said that if there is no effect modification, we expect, if that is a confounder, we expect the odd ratio to be even almost the same across strata. If there is a clear evidence of effect modification and substantial difference in the exposure disease association between strata, report this and report the exposure disease association separately in each stratum. So, of course, if there is difference in their odd ratio, their whatever you calculate, that should have, you say there is different modification and you calculate the different odd ratio for each stratum. If there is a moderate evidence of effect modification, use Martin-Hansen method, but in addition, report stratum-specific estimate. So if it is moderate, you can still go and calculate the Martin-Hansen, where you're going to discuss for confounding removing. But you still report the odd ratio for each stratum. If there's no evidence of effect modification, report this and use Martin-Hansen method to describe, close the door. Yeah, this now we have just talked about. Let's talk now. The subset, this stratification we are talking is a subset defined by the level of the confounding variable. Anyway, this one is not. I just want to now start discussing confounding, how to remove confounding through stratification. So because you do it across the different strata, that's why they call it stratified analysis. Now, the step to do stratified analysis, that step actually incorporates what you do for effect to detect effect modification control for confounder. So the first thing, there are 5 steps. Test the crude association. That is, you can do your chi-square and do your odd ratio for the whole. You have not, you have not divided them into stratum now. Just first of all know what is the association, what is the odd ratio for all the data set. So look at the effect of the exposure on the hardcore. Then conduct your stratified analysis. That is, calculate odd ratio or relative risk for each level of the confounding variable after stratification. That's the second step. So you now test homogeneity of odd ratio or relative risk to determine whether the measure of association are significantly different. So this can be done by conducting Breslow-Day test of homogeneity. So a significant test indicates significant interaction or effect modification. If this is clear, then it is advisable to report separate odd ratio or relative risk for each strata, or each stratum rather. You are making noise, Hugo. So you now calculate Mantel-Hansing odd ratio or relative risk if the test of homogeneity is not significant. So if the test of homogeneity is significant, it means that there is heterogeneity. And it means that there is effect modification. There's no need to say you are doing Mantel-Hansing, you are odd ratio relatively, because you can establish the fact that that is effect modification, not a confounder. But if that one is not significant, it means that there is homogeneous, then you now go on to calculate your Mantel-Hansing relative risk. So you now conduct Mantel-Hansing chi-square test to evaluate the significance of adjusted odd ratio or relative risk. You see the odd ratio, because what happens that when you do your stratified analysis, there will be odd ratio for each level, then there will be adjusted odd ratio, the one more like a summary odd ratio, all of them. Now, sometimes some people talk about what I wanted to say before I hold it. If you calculate the adjusted odd ratio, the summary odd ratio, and compare with the crude odd ratio, you believe that if the difference is maybe up to 20 from 50 to 20%, it's the effect modifier. Now, let's continue. How do you assign weight? Because calculating, we just want to quickly discuss on how you can use hand to calculate it before we run it. But well, since it's a workshop, because for you to subscribe for this video, you want to know some things. So we have already said that even the stratified analysis is going obsolete, but still, because the calculation we can is a little bit tricky and it will be difficult for some people to conceptualize. Something you can see conceptualize. Welcome. So now, unless it appears that the association between the exposure and outcome varies markedly between strata, we usually wish to combine the evidence from the separate strata and summarize the association, controlling for the confounding effect of confounding variable. Okay. The simplest approach would be to calculate an average of the estimate of the odd ratio of the association from different strata. That is, if after you are calculating, you are establishing that okay, it's not a fair modification, it maybe it's a confounding. You expect the odd ratio to be almost the same. Now you need to calculate a summary, that's the Mantel-Hansing odd ratio. Instead of, because if you have different strata, why are you calculating different odd ratio? So the odd ratio you have calculated you can now summarize it like more like a average odd ratio for them. However, we know that in general, strata in which there are more individuals will tend to have more precise estimate of association. That is, one with a smaller standard error. You know, I've already said before, whenever your sample size is very large, the standard error will be small. When sample size is very small, the standard error will be much. So the one that has smaller standard error, whatever you calculate there is more precise. It's a better estimate. So that's what it's saying. You know, if you divide something to just 1 minute, you divide your data into strata. They may not have equal sample size for each strata. So the one that have higher sample size, more data set there, the odd ratio you are going to calculate that one will be more accurate than the one with less number of subjects. So we therefore calculate a weighted, to make noise, if you want to make noise, go into the room. We therefore calculate a weighted average in which data weight is now given to strata with more data. So the way to do is that the odd ratio you want to calculate at the end, the summary of ratio will be something that it has weight. Look at the way it's specialized. The weighted average odd ratio will be summation weight times odd ratio. So the weight for each of you multiply each odd ratio and the weight and divide by the weight. That is, you know, we have already said that the one that is more accurate has more weight. The one that have higher sample size. So if let's say there are 3 strata now, odd ratio, 3 odd ratio for each of for each strata, 1 odd ratio. So you multiply by the weight given to it, then divide by the total, the sum of all the weight. It will now give you the average odd ratio. That average odd ratio will be the maintenance odd ratio. So odd ratio in each stratum is this one here. Then weight is given in the calculation of the weighted average odd ratio. So the summary, the maintenance, the summary odd ratio is called summary odd ratio or maintenance odd ratio. But if it's relative risk, it will be maintenance relative risk. Know that in the weighted average, the weight are always positive. The larger the value, excuse me, you are making noise. Go to the room if you want to make noise. The larger the value of weight, the more odd ratio influence the weighted average odd ratio. Also know that if all the weight were equal to 1, then the weighted average odd ratio will be equal to mean odd ratio. So the most widely used weighing scheme is that proposed by Mantel and Ensign, and that's what they call it. So Mantel Ensign odd ratio, 2x2 tables. So the way they conceptualize is this. So used to combine separate strata and summarize the association. So separate strata, you know, if you run your 2x2 table for all, it give you the crude odd ratio. When you now divide it into the strata, you have separate odd ratio for each stratum. So what the Mantel-Hansen method does is to now calculate an average for all the odd ratio. So the estimate of odd ratio for each stratum is, we are not going to that, and because I assume that odd ratio, the estimate of odd ratio for each stratum is AD over BC. I think that one, I don't think I will have, because why it is like that, I think we have discussed it many a time. So then the estimate of relative risk, because we have assumed that it is even here we have done the measure of association, and even in the lecture of yesterday, that's what we discussed, how to conceptualize the odd ratio, why it is AD. So look at the 2x2 table. You know, the outcome usually along the vertical, the exposure along the horizontal. A, B, C, D. That is the convention. So odd ratio A, this A times D over B times C. I explained it yesterday. So maybe you go and watch that yesterday's video to get here. Even not only that one, even other the workshop we have done on comparing proportion. We talk about measure of association, relative, and we explain it extensively. So if it is odd ratio, if it is relative risk, of course the relative is A all over A plus B, everything all over C plus D, which can be written because it's too many over, you can change it and write it like this. It can be written like this. If you look at it now, if you say A all over A plus B divided by C all over C plus D, A all over A plus B, if you now change this one to times, it will numerator become denominator. See, so it will just be A times C plus D over C times A plus B. And see, so it's the same thing. So the Monte-Enzi estimate of summary odd ratio and relative risk denoted as OR Monte-Enzi or RR Monte-Enzi are weighted average of the odd ratio and relative risk from separate stratum. The weight of the odd ratio of each stratum is, if you look at it, if you look at their formula, the weight is your denominator of each formula you use for the weight. And it makes sense. Because the denominator will be the total contribution of each stratum. The contribution of each, the denominator is the contribution of each stratum to the odd ratio to the total. So if you look at it, the denominator for OR odd ratio is BC. The denominator for relative is C into A plus B. So that is the weight. So it will now form the numerator. That numerator of each either odd ratio or relative will now form the numerator of their weight. Weight of odd ratio will be PC, which is the denominator of the odd ratio, over N. N is the total. Can you see? While the weight for relative rate of each stratum will be C A plus B into A plus B over N. This C into A plus B over N is the last denominator we have there. Now, for odd ratio now, since the numerator of the weight is the same as the denominator of the odd ratio, so it can be written like this. So the weight multiplied by odd ratio. So if you look at the formula for odd ratio, you now substitute this W, this weight. You remember the weight is denominator of the odd ratio over the N. So you change the formula, that's why it will be weight times odd ratio is equal to A and D over N. The same thing for this one. Okay, sorry. So when you now come, this is, sorry, this is hiding something. I have to use a lot of artifact. Now, if you now come here now, so Monte-Enzi odd ratio will be, can you see? Can you see? Weight times odd ratio. This is what we have here. The weight, the formula for that weight is this one. So this all over this. The same thing for the relative risk. So since the numerator of the weight is the same as the denominator of the relative risk, so you can write this one like this. So the the formula for the Monte-Enzi ratio, which is summation of weight times each odd ratio over the total of the weight, can be written like this. So example, we have an example so that we solve the example. So I think let's do the example, maybe you make you to understand it. And we now run it with SPSS. Now, baseline obesity and incidence of CVD by age. Or is there any question before we proceed? The one we just explained, is there any question before we look at the example? Yes?
Yes, sir.
Yeah.
Thank you, sir. That last slide, okay, or the one before, you said the numerator of the weight is the same as the denominator of the relative of the odds ratio in each chart. Like I understand, but like I'm trying to understand. Yeah, I think I must have gotten lost at some point, but I'm trying to understand how.
Yes, I know that there is a tendency for that, because that was why I myself, because I myself, you know me, I don't like emphasizing formula,
Okay.
but you know that sometimes also
Oh,
you get to understand how to even run the analysis. There is no problem, but since you may want to know some mathematics, where there's something you may not bother yourself much
No.
about.
Okay.
You want to know some mathematics
Okay.
about it, you may not bother yourself much about it. If you go back by looking at, you be able to conceptualize.
Okay, I'll be able to understand it.
Yes, you
Okay.
understand. It's just some,
No problem.
you know, algebra, just working on some algebra.
Okay.
Uh-huh.
Okay.
So,
Okay.
so maybe, okay, let me just share something first. Let me, because it's good to understand the share. Let me see. So, if you remember what I said, that so you say that the weighted odd ratio, maintain having odd ratio you want to calculate, is equal to summation of the odd ratio times the weight. Each odd ratio. Do you get what I'm writing now? Are you following? I want you to respond, please. Unmute
Yes,
yourself.
sir. Yes, sir. Yes,
So,
sir. So I didn't know I was
so each
muted.
stratum has its own odd ratio.
Yes.
You know, you multiply it by a weight, because each of them, they don't have the same. Their weight is
The
based
same
on
odd.
their sample size, the
Yes,
number
sir.
in their group, you examine that. So
Yes, sir.
now over this, now summation of all the weight together. That's how to
Yes.
calculate, because minimum is more like average odd ratio now for all of
Yes.
them. Now we now see that the formula for odd ratio, naturally,
Yes.
you understand that one, AD
I know that one.
AD over BC. Now the average, because if you look at the table, the way, okay, we leave the table. So the weight for each odd ratio and for each stratum now will be denominator, that is the total, that you know, this is what is serving as denominator for this odd ratio, for the odd ratio, right? Will be C over n is the total for that stratum. Note the n at the corner. The total sum for that stratum. So the weight, of this odd ratio should be, that is, what is this is the value of the total n for the stratum.
Stratum. Yes.
Over this.
Yes.
So if you are considering, instead of odd ratio, relative risk, it's still the same thing.
Same thing. Okay. Okay.
Is it the same thing like this? If it's relative risk, it will be the Martinezin relative risk will be sigma, the weight of each stratum, as RR, relative risk.
Okay.
And the formula for relative risk is this. After we have written, it can be written like A into A over A plus B over C into
C plus
C plus D. But this thing can be written, if you change it can be written like this. A over C plus D.
Oh, I see. Yes.
Over C over A plus B. And if you try to change it,
Get
you
this
remove
one.
that division, you remove division
Yes.
to make it times.
Division to multiply. Yeah.
So if you do that, so the weight for this one also will be, for this one will be C into A plus B. You know, it's just some mathematical they just play with here. Over N.
Okay, I get this.
So what is that saying that instead of writing this, since we know this one like this, you can as well this this one is the denominator for this one.
Yes.
That means that you can as well say this one, if you cross, you know, anything over something is over 1. This one means over 1.
Yes.
You can as well say BC or W minus N in times N. No, you can, if you cross multiply.
Cross multiply, yes. WN equals to BC. Yes.
So in that case now, that is what inform, you can as well write here and say WOR times OR equal AD over AD over N. I don't know if you understand now. AD over N. So instead of you know, if you look at this one now, when we want, because if you write this one will be
yes.
One can as well be N.
That's true.
Is equal to BC over W.
Yes.
So here, when you have the W here, I don't know if you understand, or W, whichever way. So you cannot substituting. So W come here instead of this here. You just put N here.
The B, yes.
So what? Because it's, I don't know if you understand me. Because BC, that BC you replace. That is what I'm trying to say. This one you can replace this N. No, this BC with WN.
Yes.
If you say OR, this formula now you say OR. Why is it not? OR is equal to AD over BC. You can replace the BC instead of with WN.
Yes.
AD over WN. So if that's the case, if you cross multiply AD and this one, so you can now this one and this one will now leave. You can move this one here. That's what has happened. To move this one here, just some step of mathematics. So if you cross multiply here, this one is over 1. AD, or you say ORWN, WN multiplied by OR will be equal to AD.
Yes, sir.
So you now say WN OR is equal to AD over N. That's what brought this one. I don't know if you understand now.
Yes, I do.
It's the same thing. If we work it out also. So that is just because sometimes it can be confusing. But just know that it's one part of mathematical. If you sit down to understand this, yes. So that was what brought. So the one. So when you now see this formula, which is we have written before, that maintenance odd ratio is the summation of each odd ratio and the weight over summation of weight. So we have already substitute here. So this one now, WOR is the same thing as AD all over N. You now replace it AD all over N. I will already know that the weight, the summation of weight, the weight is BC all over N. I don't know if you so you now put this over this. So that's what brought this formula. The same thing manipulation go for what do I call it? relative risk. So the same way. So let's look at the example and solve it. Based on resident incidence CVD. So if you look at this data now, the last part of the data, overall, the data set is one. There are 1,000 people and 46 are obese. Can you see? And 300 are obese rather. Can you see? 300 obese, 700 not obese. Then 106 have cardiovascular disease, 894 did not have. Total is 1,000. This is overall. But when we split it into two strata, people that are less than 50-year-old, and because age is a confounder, maybe it's a confounder or modifier, we don't know. So we want to look at the effect of age now as a confounder, confounding the relationship between obesity and cardiovascular disease. I don't know if you understand now. So try to split the data into two. For the for the age less than 50. So we have out of the 300 total that are obese, 100 and are less than 50, 200 are more than 50 and more. Out of the 700 that are not obese, 500 are less than 50 and 200 are 50 and above. And out of the 106 that have cardiovascular disease, 45 are less than 50 and 61 are 50 and above. Out of 894 that don't have cardiovascular disease, 555 are less than 50 and 339 are 50 and above. This is the data set. I'll call you back. I'm in a lecture, please. So now let's quickly look at, if you remember the step in calculating this thing, we have listed them, the step. So if first for calculate the crude, see here, we just decided to calculate both odds ratio. Can you see the table? Odds ratio, relative risk. So the step, this is the crude, overall is the crude now. Can you see? The odds ratio is 193 and relative risk is 179. Are we together? Are we together?
Yes, sir.
Yes,
yes.
We are.
Yeah,
I'm looking at the overall.
If you look at the overall for the same data set, you have different value of odds ratio and relative. If you remember what we discussed under odds ratio and relative when we were doing our workshop, we said that when relative risk is greater than 5, the value of odds ratio is greater than relative risk. Can you see? Relative risk is 1.79, odds ratio 1.93. Therefore, a particular data set, if relative risk is 1, odds ratio will be 1. That is when they are equal. And that is when there's no association between the disease and the exposure of interest. Relative risk and odds ratio will be 1. Then when the value is above 1, the odds ratio will be greater than relative risk. It's always greater than relative risk. When the value is less than 1, the odds ratio is usually less than relative risk. Can you see? Because we know that the odds ratio has a wider margin. The relative risk has a narrower margin. I don't know if you understand. Please. This is your goal. So you can see the crude. So you can focus your mind on odds ratio. Just forget about relative risk now. Because most of the time is maintenance odds ratio, but sometimes you can calculate, you can do the relative risk. So, but let's focus on that odds ratio. This is crude odds ratio. Now, if you split the data into two, you can now see, look at the value. But you see that are they the same? If you look at it, the value, the odds ratio is 1.93. When you do separately for each value, none of them is even up to 1.93. One is 1.48, one is 1.54. Can you see? It shows that something has either is effect modifier or a confounder. Reduce your volume, please. or effect modifier or confounder. Whichever one, it is the one that made this group. It has amplified the effect of this obesity on cardiovascular disease. So this age, whether it's serving as a effect modifier or as serving as a confounder, the age distribution is affecting it. It's giving impression that the odds ratio is big, whereas it's not as big naturally. I think you can see. So if you look at the Martin-Huntington odds ratio, if you look at it, you see that when you calculate it, it's 1.52. Can you see? It's more like you know, it's a summary, it's a mean. So it will be something between these two. You know, it's to summarize the two to find average for them. So it will be a value in between the two. So you can now say that this is the adjusted odds ratio now, 1.52. You have adjusted. So, but when we run it, we discuss further the issue of modifier all those things. We just run it because when you bring the output out, you get more revelation about it. So this is similar thing for look at it. Look at relative risk. So the value also you get is lower than what it was given you before. But when you summarize, is look at it. Same thing like this. No, maybe more than maybe because of the way we approximate it. I don't know if there is any question. Let's go and run it before we discuss further. Let's run it. So the data, okay.
So sir, in this case, are we going to call, like, by just visualizing it, can one make a deduction of whether this could be age could be an effect modifier or a confounder, like in this case now?
Yes, thank you. That's a great
by visually.
Okay. Yes, the issue there is that most of the time, because when we run with hand, for us to go and see if it's significant, we have to go and be looking at the table, yes, and the word has gone beyond that. That was why when we run it now, that if you look at the step I gave before, we are going to assess the story. You're going to see those steps, it will come out because those Breslow tests will come out. So it's only that I didn't want to bother us with all those. You know, you have too many tests here.
Yes, I said that.
Exactly. So, but when you just follow, all you need to do is follow this step. We have calculated the crude odds ratio now. We have calculated the certified odds ratio. Homogeneity test is for us to do the Breslow test. We will run it now. If we do the Breslow test, if it's significant, because we can you can see that they are different, but those different, we don't know if they are statistically significant. No, we can see that it's different across paper now because there's 1.48, 1.54. There's a difference. It means that because they are supposed to be the same. Since there's a difference now, but if that difference is statistically significant, that should that is an effect modifier. But if it's not significant, that should that is confounder. Does it make sense?
It does. It does.
So let's run it.
So it's not enough to visualize.
Yes, yes, you have to put it to test because you can.
Thank you.
When you say
you have to put it to test.
If you say something, it doesn't have to be the same number. It doesn't have to be the same. When you say something as similar, it doesn't have to be exactly the same number. But when they are different, and when we say that it's the same, when we say it's not the same, you know, that's why we do statistical test. And that Breslow something is another something which I don't want us to dabble into the mathematics behind it. But let's just run it, you see the result. So you can share. Are you using your laptop now? Or is your phone?
Yes, I am.
Okay, you can share that.
No, I'm using my laptop.
Obesity, the data set. Obesity and cardiovascular disease.
What disease? Okay. I'm just going to open it on my desktop.
And I'm happy that before your exam, we are able to do this one because
I'm so happy. Like as if yes, we initially were saying, I should call, but this kind of forum is very good.
Yes.
Like the way
So,
everything is being explained. This is clean
exactly.
and yes.
So if you, by the time you understand the logic behind those, by the time we do the logistic regression, you understand. In the exam, you just be looking at them.
Exactly.
Just be, and it's your discussion that made them to know that this one know what he's doing. You don't need to know everything anyway, but when they see that you are not alien to what they are discussing, the examiner, or it's not alien to you,
What
what they are
saying.
discussing, you have, even if you don't even know everything, you have understanding to certain level.
At least you have an idea.
It's not even more than idea. You have some understanding. You know that this one is different. The examiner. You know, when we were doing our part two,
I want to share. Okay.
Okay, share.
Uh-huh.
When we're doing our
It's
part
not
two.
allowing me share.
Okay, sorry, I have not allowed.
Host disabled.
Let me do that. So you can share now.
So you were saying when?
Yes, we were doing exam.
You were saying something, sir.
Yes, when we were
When
doing.
we were doing your part two.
Part one. No, most examiners will say that, where are you training? No, after you have done your oral something, they say, where are you?
That's true.
We will ask you, where are you training? See here.
That's
So, say, where are you training? Where do you train? So, is the understanding.
Why did they do that?
Okay. We amused ourselves. We amused ourselves as examiners. It's time for our laughter.
Oh, okay. I now understand. Okay. I thought it was beyond. I thought maybe there was something else. Okay.
Oh,
Can you see my screen now?
No, we just use you people to laugh.
Oh, okay. I now understand. Because I was like, because I knew they asked that. I was like, I used to understand. I didn't understand. Okay. Now I get.
No, prof is talking from experience.
It's for our own enjoyment.
Yes. So, you have failed some people until they come and prove otherwise that they can pass. And you have passed some people unless they come and prove that they will fail. That's what they do. Because the examiner will have made up his mind.
No, everybody has failed.
Until
everybody has failed.
All right. So can you see my screen?
Yes, you can see. Yes, thank you.
Yes.
Okay.
Yes.
If you look at it, this data set, we'll use it tomorrow also. But if you look at it, I put some aspect. If you look at it, we have the serial number, the age group, the obesity, and CVD. Those are the ones we are using now. Why the other one I do it for logistics? You know, I told you.
Yeah.
I told you, if I did last three now, that's what we're going to use for logistics tomorrow. This first, this other one, we are going to use it for now. If you go and use this one, the logistics, it will give you wrong. No, if you remember, the table A, B, C, D, they have address. Those 2 by 2 table, A, B, C, D, they have address. And what I did to code for all of them is obesity, CVD, is to say, okay, obesity, obese 1, not obese 2. Yes, I mean, so that it will arrange the one obese and put it in A. I don't know if you understand me now. The one that is not obey and put it in B. If I use 1 and a 0, it will put the not obey in A and put the obese in B. I don't know if you understand me now. So you need to know how to to enter your data. But when I want to do the regression now, I have to code the obese as yes and not obey as 0, and code the CVD as yes as 1 and no CVD as 0. But for this one, we want to do now is 1 and 2, 1 and 2. If you go and code it 1 and a 0, and you get wrong answer. So okay, go to analyze now. Go to analyze. Go to analyze. Are you there?
Okay, yes, I am. Okay, I am. I was trying to unmute myself so that I'll be able to.
Okay.
Can I see my
Yes,
screen?
yes,
Yes,
go to
yes,
analyze.
yes.
So descriptive, descriptive. We are not going to do regression. Descriptive
Okay.
cross tab. You know, anything that is has to do with 2x2 table is on that cross tab. Click Control.
Yes, that's true.
Yes.
Okay.
So move the row obeys as the row, the exposure. We want to first of all do the crude one, obeys as the row. Then do the CVD
Age.
as a column. No, leave age for now. We want to do crude. I don't know if you want to do crude first. So statistics.
Okay.
Go to statistics.
Okay.
You see concrete. No, look at Mountain Hansen. Mountain Hansen.
Yeah. Yeah. So that's what it is for.
Cochrane Mountain Hansen.
Click on, well, I don't even know if you even need to click on the risk. Click on the risk.
Okay.
Okay. Click on the risk. Remove that Cochrane Mountain Hansen because we just want to do crude now. Just remove that Cochrane.
Okay.
We just want to know the crude. Click continue.
That's all. Okay. Do I click OK?
Yes, continue. Okay.
Yeah.
Okay, I have to stop sharing.
Share the result, yeah.
Sorry.
Yeah, share the result.
Can you see it, sir?
It's coming.
Okay.
Yes. Can
Not yet.
We have seen it.
Yes.
Okay, you can't see it yet. Okay.
You can see it. Scroll down.
Okay.
No, it's okay.
You can see the odd ratio now, 1.93.
Yeah.
If you remember what
this way.
Can you see the odd ratio? The crude odd ratio, 1.93.
Yes.
Can you see the crude odd ratio?
Oh, yeah.
And it's significant because the confidence interval does not cross 1.
There's no
And
cross.
look at the relative risk 1.79. Can you see? Can you see relative risk? That for course,
Yeah.
yes. If you remember 1.79, can you see? That
I
was
remember.
Yeah.
So this is crude odd ratio and relative risk now. Now go back. Go back.
You have to stop share or go back.
No, don't stop share. Just use analyze from here. Click on analyze.
Oh, I see. Okay. Okay. Then go to descriptive.
Yeah.
Cross tab. Then go to that statistics, Abby.
Yes.
No. We want to use age now.
No, we are not using. We don't want to run age separately. So bring age now as the level. Move age here to the level layer. Exactly. Layer. Then click on that statistic and go and click on the Mountain Hansen.
Do I remove risk or do I leave it?
No. Leave it.
Okay.
Click on Mountain Hansen.
So can I?
You don't even remove. If you don't even click on the list, you still do. Just continue. Don't worry. Just continue.
Okay. So I click OK.
Yeah.
Should I click OK, sir?
Yeah. Yes. Click OK now.
Okay. Can you see it or should I stop sharing?
Stop sharing and we cannot see. It's still stationary.
We can't see the result. We can't see the output now.
Okay. Tell me where you can see it.
Yes.
Yes.
Scroll down now.
To the risk estimate.
Go down. You can see.
If
you remember, okay, before this one, scroll up. There you went to down. Scroll up. Let's see the initial table.
Okay.
It's okay, yeah. No. Just Scroll down, see. This is the one we run before.
This one. This one you want.
You be going as small. You know, you see, wait. Wait. Don't run too much.
A little bit. A little bit up,
See.
yeah.
A
little bit.
Up a bit.
Okay.
No, it's okay.
Okay.
You will see that the odd ratio for, if you remember, for the less than 50, if you remember, it's 1.48 we got, you remember?
Yes.
And it's no more significant now. It's not significant because it has crossed 1.
Oh, let me see. I can't see. So this is
Look at the confidence interval now. Confidence interval.
Yeah, 0.7.
Oh, that is true. It has crossed
0.7 to 3.
It's less than 1.
Yeah.
Oh.
No, it has crossed 1. Yes, it's less than 1.
It has gone beyond 1.
Yeah.
The same thing.
No, what I mean is that 0.706 is less than.
It's less than 1.
1, so it has crossed 1.
And look at
the
this
range.
Look at this one. Odd ratio for greater than 50.
50 plus.
If you look at it, it's
1.5.
1.54 we got also. But it's not significant also. Can you see? So because the odd ratio, after you have done the startup for each startup, the odd ratio is not significant for each startup. But when you put all of them together, the odd ratio was significant. Now you want to see, we see that we have different value now. This 1.48, 1.54. Are they the same? Are they actually the same or they're significantly different? Look at the Breslow test of homogeneity. It's not significant. It's not significant.
So where did they get it? 1.54? Okay, I've seen it. 1.8, 1.54.
Okay. Look at the Breslow test of homogeneity. It means that it's not significant. That shows that it's the same. There's no difference. These values are not too far. They are not different.
So what was the odds? Because this odds ratio, that's the total odds ratio was significant. If you just look at this lower
all this one not significant. But what we
that's the crude.
The crude, I mean.
But what we are seeing now, what we are looking at now is this different. This stratification, 1.48 and 1.54. Are they the same? Is there any significant difference in the strata? So this Breslow, no, there's no difference.
No.
If there's no difference, it's telling us that it's not effect modification. If there's difference, there's effect modification. So it's not that age is not, it's a confounder. It's a confounder.
Not effect modification.
So it's age actually that made that thing to be significant. That obesity causing cardiovascular because the people that are old, they are more likely to have cardiovascular disease. It's not because
sorry, I think get this place quite right. Okay. So 1.47 and 1.54. You said the two of them are not significant. I want to explain it again. Let me see.
What we are saying that
look at the breast. Look at the breast there. Look at the breast load there.
Okay, before breast load, Prof.
No, it's trying to. Okay.
There are two things we discussed. Maybe we don't know which one he doesn't understand. There are two things we are discussing now. Number one, we first of all look at odd ratio for each stratum. If you even see the total odd ratio is still there, it's still DD for us. The total odd ratio is still there. Look at it.
I said the less than 50 and the more than 50.
Wait.
The total.
The total is 1.93 and is significant.
Okay.
It's giving impression that obesity is a confounder. The people that are obese is a factor. The people that are obese, they are 1.9 times, almost 2 times likely to have cardiovascular disease than the people that are not obese.
Have cardiovascular disease.
The source is significant. But when we now split it into 2, you do it for less than 50, greater than 50 and above, you look at their odd ratio. Number one is slashed down. The odd ratio of each of them is not up to 1.93. The odd ratio for each certain one is 1.48, one is 1.54. Now, for each of them, they are not even significant. Can you see? because look at the confidence interval from 0.7 to 3, it has crossed 1. Look at the confidence interval for this one, from 8 to
0.8 to
2.6, it has crossed 1. So even though for the total it was significant for each of them, apart from the value is very low, is lower than the total, they are not significant. That's the first thing. So now we want to see that show that age is what made it to be significant before. Now that we are split it for different age group now, is no more significant for each of them. But we want to still know that this particular age is C effect modifier or a confounder. The step we want to know if, let's say, each odd ratio for each stratum, they are close. Because if it is confounder, they should be close. They should be the same. If they are not even the same, they cannot be any different. So the value we are seeing 1.48 and 1.54. Are they the same or they are different? So the Breslow-Day test is the one that is helping us to know if they are different, if there's homogeneity. But we have already seen that there's no significant difference in the two, because look at the p-value, 0.93. So if they are different, if they say they are different now, that shows that age is effect modifier. But now that they are not different, it's a confounder. Because if it is a confounder, the odd ratio, when you do the odd ratio for each of the strata, should be the same. They should not be different. But if it is due to effect modifier, the odd ratio will be statistically different. The two strata will be different. Does it make sense now?
Yes.
Yes. Now, let's move down. See, let's move down. Let's move down. Scroll down. Oh, no, okay. Well, let's see the head. Now, look at the Martin Hessing. If you look at the estimate, the Martin Hessing odd ratio we did, it was, if you remember, 1.52. The one we calculated. If you remember, or should I show you? It's 1.5.
No.
It's 1.52. The final, the adjusted one is 1.52. So you see, if we have already established the fact that this is not effect modifier, though people say that the test is the power is very okay. There's another even chi-square we talk about. Look at that chi-square. There's a conditional before.
Is it the one? The Cochrane's one?
No. There's one. Okay.
Okay, let me go up.
No, that's it.
No, that's a conditional independence.
It's there under Cochrane. That chi-square. Conditional independence. Can you see?
Yes.
It's still confirming that it's not effect modifier. You understand now? No, but the issue is that if you look at it, it's almost significant. With 0.0 something, it's almost significant. No, sometimes they say that the test is the power is very small. But the fact that this doesn't mean that there is no effect. But just assume that it's not effect modifier, age is a confounder. So look at the estimate. The estimate is 1.52. So let's see the crude between the crude.
Hello.
Yes, sir.
I have missed one step.
Mr.
This test of conditional independence. How is it not a modifier? Explain that, please. Let me see.
Okay, I'm coming. I want to stop sharing. You go stop sharing first. Dr. Iguilo, stop sharing. I want to share. Okay, so look at the last conduct materializing chi-square to evaluate the significance of adjusted odd ratio. If the adjusted odd ratio is actually significant. Okay, I think that is the last one we did. So is the best, sorry, is the best law that told us that it's a Fed modifier or not. But this the chi-square is to test for the significance of the adjusted odd ratio. Is it significant?
Okay.
Yes.
Okay.
So you can share now. Share.
The output.
And share the output. So if you look at it, you say it's not significant. It's almost, to me, it's almost significant. The effect of the adjusted odd ratio. But what I want to calculate is that let's look at the difference between the adjusted and the crude. The adjusted odd ratio and the crude. Let's calculate. You know, the other one is 1.93. The adjusted is 1.52. The difference is 0.41. 0.41 divided by 1.93. Yes. So if you look at it now, is
that how you calculate the adjusted? What you just did now?
No, I'm just trying to see the crude odd ratio now. I mean, some people, they say that they usually say if the I think maybe tomorrow I will supply it because there's more information I will try to get. I will say they were talking about the effect modification issue, the figure. Some people talk about 15%, 20%. Well, I will discuss that one tomorrow. Don't worry. I don't let me confuse you. I will get the information tomorrow. Before tomorrow, I will discuss it. So this is what we have now. So you can see that, well, it's trying to tell us that it's not significant, but that the effect of the adjusted is not significant. But we are going to run the same thing. We are going to run logistic tomorrow. We're going to use the same data to run logistic. Part of the logistic we want to do. We run it as logistic. We're going to understand further. So stop sharing. You can
no. Before we go, sorry. Sorry.
Okay.
Hello.
Go back. Yes. Go on, sir.
There are two 95% confidence intervals with lower and upper bounds. In the last.
One is talking about odd ratio, one is talking about logarithm of the common odd ratio. It's logarithm. When we want to discuss logistic regression tomorrow, we'll talk about that because logistic regression is all about logarithm of odd. So the other one is log odd. It's not yes, it's just talking about the log odd. And actually, to calculate the confidence interval, that's what they usually use to even calculate the confidence interval. So we'll discuss that log odd tomorrow. Okay. So let's take it bit by bit because I don't like discussing something that makes you, because there are some things you should just pick, and those are the most important things. If we look at this concept, you don't need much mathematics about this. Just understand this thing and know how to run it and interpret the result. So like that best law now, once best law is significant heterogeneity, it means that it's a effect modifier. It's effect modifier, effect modification. So in that case, if it's significant, it's effect modifier. You don't need to talk about this confounding or whatever. You report each odd ratio separately. You don't bother yourself about the adjusted odd ratio. It's not useful. Yes, you report separately because there is interaction. So you have to report each of the odd ratio separately because it's believed that they are separate, they are different. Okay, let's. Now, sometimes you may try to look at the stratification we do now. We stratify the A into 2. But you can decide to stratify D into each of these. Can you see? Into different groups. Imagine we did the age now into 5 groups or 6 groups rather. You can do that. So maybe what I will even do before tomorrow, I will maybe the data, because I didn't do that before. I will certify it. We see what I will try to create the data, or we can even do it now if you, but it may waste this thing. It's just to look at those that are 30.
5 to 39.
We can even do it. Don't worry. We can even do it. Don't worry. Let me just finish talking. We can go and do it. We can do it. I can ask her to share. We do it together. It's part of learning. This is workshop. Now,
Recording.
yeah, it is 40 years. You just to create another variable 2. You now recode 6 strata and use it and see what it will give us. So certification. It is possible to apply the Martin-Enzi method to control simultaneously for effect of more than one confounder. Like this one, we can say, apart from obesity, you can say male, female. Yeah, I don't have that data of male, female. You can say male, female. You can say family history of the heart disease, no family history of heart disease. Can you see? So in that case now, you are having look at the other one, the way we split the age. We can split the age into 5, 6 groups. We can use this one to split this one into 4. Can you see? Using 2 variables at the same time. Still further also, you can even look at it. You know, once people are saying they are controlling for confounder, you may have gender as confounder, age as confounder, smoking or smoking, many things as confounder. Can you imagine? Male, female, gender, age group, 5 of them. Then smoking, 3 levels of smoking for each age agenda. Can you see? It will now give you 30 different substrata. So when you begin to do that, it will be cumbersome you interpreting when you are having too many variables. So that is why the alternative is regression. Can you see now? Can you see where I'm going now? Yeah. The alternative is regression. It's the same problem you have when you are doing ANOVA, when you have many groups, especially in factorial ANOVA. When you have many groups, you have this, you have too many groups. Interpreting it, running it, it's cumbersome. So if you just do regression, yes, regression will take care of it. It's the same thing here. The stratified analysis, that's why it has given way to logistic regression. I mean, there's no point. So you are doing this thing. It has given way to logistic regression. So let's Ugo, share your data. Let's go and do that thing. Share the data again. Share your data.
Okay,
Yes.
sir. Okay. I don't know if you can see it.
What's wrong with me, sir? I thought I have the something. I don't actually have the data for the 35, but because where I got it, I don't have the age group.
Okay, don't have.
I have 2 years. 2 years. I just have. Sorry. I thought I would be able
to have got the principle.
Okay.
We've got the principle. I think that's more important than the actual figure. We've got the principle.
Then what I wanted to ask is when analyzing those, when analyzing in those layers,
go on. Ask your question.
Okay, my question is because it's beautiful. I like the way you explained using those visuals. It made good sense. What I'm trying to ask is that when you want to analyze it in terms of, are you going to take each of them apart? Or
no, that was one. Don't worry. If I'm able to get more data. That is
data. That would be good.
What is there? What is just there is very simple. What is the age now? The age.
Yes.
I have the raw age.
Okay.
I have the raw age. What 30 to 35? Okay. We just mark it 1. The other 2. We now have about 6 group. We group the age into 6 groups. Yes, I mean, instead of 2 groups. And when we want to now run it, where you put that layer age group, you just put that one. So this age group now, there are 2 strata. But that one, there will be 6 strata. Yes, I mean,
but it's still the same.
If you use more than 2 two variables. Layers. You
okay, but is it variables or layers? Sorry.
Yes. Oh. You now put, if we say history, like the one I say history of this, yes or no, you put it. You say next, press next. You now put sex. You now put. So if the history is yes or no, sex is yes or no. If it has given you 4 groups, it will run it for us like that.
Wow.
And yes. So don't worry, I will try to look for data. Maybe
I now get it.
Tomorrow we quickly run that up. So that's just the, even if you say you have such data, you can go and run it. It's just the logic to get the logic. Once you get
the statistics, you
what did you say?
Put the, and when you go to the statistics, after imputing those things, you come here, put the Cochrane, and then the risk.
Even the risk here, you may not, if you put, you may not even need to put it. It will calculate it for yourself.
The risk is not necessary
for you. Do without putting yes. So it's very straightforward. And if you want to calculate chi-square for them, you can put that. You are not looking for chi-square now, and that is all you are looking for. So tomorrow we'll be looking at this data. Also we use it, but we'll be looking at the logistic question, and some basic concepts. Maybe you can I can actually just use this time to discuss it. No, you can stop sharing, because that one
don't stop sharing. Just hold on first.
Okay.
Please go back.
I said you should go back.
Go back. See that table. I just want to understand how it is coded. Age less than 50 is 1, more than 50, maybe 2 is under, below.
Scroll down.
Is that correct? 2 is down.
Scroll down. Yes. Let us scroll down.
No, there's no point. There's no point. Obesity.
So that you can see it now.
No, yes. I have understood now.
The same obesity 1 and 2.
Okay, but you gave a cutoff using the BMI. Did you use BMI?
No, where they will have used the data.
In the raw data.
I got the data from somewhere. It's not, the table.
Okay, it wasn't from you.
Table on table. The table is me that. They have already. If they put something table by contingency table, you can enter it.
Okay.
That's what I did. It's on
then this CVD,
where I got the data on contingency table. I just entered
1 and 2. The CVD 1 and 2. Which of them have CVD?
Why is 1? If you go to the label.
1 CVD, 2 no CVD.
Go to the label. Go to view. You see 1 is CVD, 2 no.
No, I'm done.
If you don't do that, yes, you have to do it like that. Then if you look at the one we now want to use for logistic, I have to code it 1 and 0. So the one you are using for the class tabulation, the coding will be different from the logistic. Okay, now, Ugo, you know what you do? Let's go and run the same analysis you run now. Use the logistic coding. You see, it will give you different answer. Use the logistic coding.
Okay.
It can cause problem for you. It can invert the answer. They invert it. Though eventually you may get some statistic the same, but click OK. Let's see what it gives. Scroll down. It give you, if you look at it, it give you the same answer, But it give you the same answer because both of them they are parallel. You get the picture now. But in the go up, there's something that
this one.
Yes, I will. Call logistic. Where did we get? Is there any place we get? Okay, yes, we calculated. Okay, we didn't look at the relative risk. So sometimes it can lead, because it can invert. Why it give you this answer is that at least you are able to get some answers that because for both sides you coded a 1010. But if you are tabulating it now, it can cause confusion. You see where you put the yes, where you put the no. No, you get the picture now. Normally yes should be up and no down. That's why it's good to follow the convention of the coding. So let me quickly, you can stop sharing. Let me quickly open some discussion. We can end there. And I guess tomorrow.
Thank you, sir.
Welcome. Yes. Yes. I just want us to quickly discuss some, though this thing also I said yesterday, I presented yesterday, so that we get something right about probability, risk, and logic. Because tomorrow, for you to understand the logic behind logistic regression, you need to understand the relationship between probability, odds, and the logic. The odds is the logarithm, and the logic is the logarithm of the odd. Now, this is the probability that a particular event or outcome will happen over time. We know that one. Probability is risk. And we have established the fact that probability, odd is risk all over 1 minus risk. That is, odd is probability that event happen over probability that event will not happen. So risk is the probability, while 1 minus risk is the probability that the event did not happen. Risk is the probability that the event happen. 1 minus risk is the probability that the event did not happen. So odd is risk over 1 minus risk, which means probability that event happen over the probability of non-event. Probability of event divided by the probability of non-event. Like for example now, if you say the proportion of women in a group is 70%, 70 over 100, that is 70%. The odds of you having a woman there will be 70 over 30, or 0.7 over 0.3, because the probability that the woman is there is 70. The probability that is not a woman is 30. 70 over 30 will be the odd. If you say what is the probability of men there, it will be 30%, and the odd of men will be 30 over 70. Now, because we know that the probability, you can see, you can have it from, if you express as percentage between 0 and 100%, you express it as fraction between 0 and 1. It cannot be greater than 1, cannot be less than 0. The odd is from 0 to infinity. As you can see, if you start calculating from 0 and begin to increase the probability, calculate the corresponding odd. You see that when odd, I said it yesterday, when probability moves from 0 to up to halfway, 0.5, the odd is 1. So if probability is 0.5, the odd will be 0.5 over 1 minus 0.5, which is 0.5 over 0.45. That is 1. So when probability moves from 0 to halfway, because the highest is on 1, you move halfway, the odd has double movement from 0 to 1. When the probability now moves from that 0.5 halfway to 1, the odd moves from that 1 to infinity. So if you show it as a graph, look at it, if you plot probability odd against probability, can you see? That's why, you know, probability here, odd is vertical. Look at probability along the horizontal. You will see that, you know, the probability cannot be greater than 1. This is a scale. So the scale of probability is 0 to 1. Can you see? And the scale of odd is from 0 to infinity. You know? So this one is fixed 0 to 1. But for odd, so it can still be more than 50. And that is why when they look at this graph, when the probability move to 0.5, the odd move 1. Can you see? Between 0 and 5. That just move just 1. When the probability now move from 0.5, to close to 1, the odd move to infinity. That's why it will not touch that graph. It begin to move it. That's no end. Can you see the plot of odd and probability? So because of that problem, the intelligence, okay, how do we solve the problem? If you, okay, before I talk about that, there's another graph that I have. This graph also is trying to show you if you plot the probability, even if you know, when we discuss about sampling distribution, even the probability followed the binomial distribution. If you take sample many times, if the sample size is high, you take many, the sample size is high, the proportion, the probability will still follow normal distribution. Well, look at odd. Can you see? Look at it. Cannot follow normal. Yes. Look at the graph of the odd. It peak here and flatten up. Where it peak here, you know, if you look at frequency, then the other. If you look at it, the scale for probability is 0 to 1, cannot be greater than 1. The odd 0 to infinity. That's why there's no end to the scale here. Look at it. It can never be. So the only thing you can do, intelligent people do, okay, to solve that problem, why not calculate the logarithm? If you calculate the logarithm, because the logarithm of 1 is 0. You know, the value of odd is from 0 to infinity. The logarithm of 1 is 0. The logarithm of anything, maybe anything that, what do I call it? 0 point something, 0 point something, 0 point something, it gives you negative. Now, look at anything greater than 1, the log will give you positive. So, what you do now, if you now transform inside of that log odd, you transform that log, the odd is p over 1 minus p. You now do natural logarithm. If you now plot it again, probability now, look at it. It will start, look at it, from infinity on the 0 side to infinity up. Can you see it? Then give you a sigma graph that look better. In another way, if you plot it, it will follow normal distribution better from infinity to infinity. From negative infinity to negative infinity. So there is, I think there is something I have here also, and I show that. Look at this. What I try to do here is this probability, this is a log. It's not actually a logarithm of this. If you do logarithm of 0.01, and you see minus this, logarithm of 0.99999, it will give you this. So if you plot it, if you plot the like this, if you plot this one, I look as it follow normal distribution. So logarithm of p probably 0.5 is 0.
Is 0.
Yes. So logarithm of if you now come back, I want you to look at another fact I want you to know about the logarithm, just to prepare our mind. sorry. The logarithm, the log of odd, the logarithm now, what it does is that, let me just, when we refer to likelihood of having an attribute or proportion, I think I've explained this one. What I just want. Logics are important because the difference between the logarithm of two quantities is equal to the logarithm of the ratio of the quantity. That is, if you say logarithm of A minus logarithm of B, the same thing as logarithm of A divided by B. Look at an example here. I put logarithm, the value as type 1 to 20. I did their logarithm. Look at their logarithm. For example, now, logarithm of 6 minus logarithm of 2. It will give you logarithm of 6 over 2, that is logarithm of 3. Look at it. Look at it. What is logarithm of 6 here on this case is 1.79 on this case. What is the logarithm of 2 is 0.69. When you remove 0.69 from it, it gives you 1.1. And that is the same thing as logarithm of 3. Can you see? Which is 1.10. Can you see? So the issue there is that you know that 6 minus 2 naturally is not equal to 3. 6 minus 2 is not equal to 3. Because if you say 6 minus 2 is 4. If you say logarithm of 6 minus logarithm of 2, it's the same thing as say logarithm of 3. Can you see? Logarithm of 6 and logarithm of 2, the same thing as say logarithm of 3. So that's it. Logarithm, or the difference between the logarithm of two numbers is the same thing as the logarithm of the ratio of the two numbers. When you say different, you are removing 2 with the two numbers. But when we say ratio, we are dividing. So if logarithm of 6 minus logarithm of 2 is the same thing as logarithm of 6 over 2, that is logarithm of 3. So what this one is telling you is that you're going to see the one that logistic regression, because the outcome is categorical, you just assign 1 and 0. So there's a limit to the variability in their value from 0 to 1. So it's fixed. And you want to, if you want to predict that particular from the predictor, that you can use continuous variable as predictor, but the outcome variable is dichotomous, either 1 or 0. So it's already fixed. We are going to see that the method you use now is a little bit different from the least square method you use in the linear regression. So I don't want us to, so tomorrow we'll look at that. Let's just stop here. I don't know if we have questions, so that we just stop. Tomorrow we full force on the logistic regression. I think we have an understanding of stratified analysis. Hello? Any question?
Oh, we're okay.
Okay, that's great. If you're okay, tomorrow then, you can malfunction. So I think it's more exactly tomorrow. And even the same data set, maybe I'll get another data set also we'll use. So I will still send that data set to you for the logistic. Who is making